Let us begin lecture 31 and we will continue on kinetics of corrosion. So, we have seen I0 on metal surface for this. So, like that we have I0 for everything, every reaction, and that time we have to mention the metal surface because that reaction is taking place on the metal surface. So, now let us look at this from this classical rate theory. Since classical rate theory says that there would be jump of metal atom from one surface to another, and this is a thermally activated process. So, that is what it has to have a barrier which is called as activation barrier, and then once it crosses that barrier it goes to the other surface, and this barrier height decides the rate at which this metal would go from one surface to another. When we dip a metal in a solution, aqueous solution, this is metal, the metal ion forms. Metal ions forms. Now, these metal ions would keep forming, but at the same time when it released to the solution, it will leave negative charges on the metal surface. So, you are having a situation, this is metal surface, metal ions would go to the solution, or instead of Mn plus, let us put in the form of positive charge. So, we have positive charge formation, and then we have to maintain the neutrality. So, the negative charges will be left to the metal surface, and these two would try to balance each other. Now, when this forms, then of course, the reverse reaction also forms. Now, after some time they reach equilibrium. Or reversible. Or I would say that it establishes I0, and then because of this electrostatic interactions of positive and negative charges, they would form a kind of surface on metal surface as well as on the solution surface, very close vicinity to the metal surface. And that time we have two boundaries, and that boundaries or two surfaces, this is one surface and this is another surface. These two surfaces will be in close vicinity and they will try to cancel out the charge, they would try to balance the charges each other, and these two layers are called electric double layer. electric double layer. And this was the very fast concept of electric double layer, and it is termed as Helmholtz double layer. And the inside part is called IHP and outer one is called OHP, and then IHP is nothing but inner double layer, inner Helmholtz plane, and OHP outer Helmholtz plane. And when this double layer forms, it is associated with a capacitance, and since they are charged surfaces, we have a potential difference creation, and these potential difference is nothing but the electrode potential. Or the potential on that metal surface for that reduction reaction. Now, these two planes, this is a very primitive concept of electric double layer, and then later on this has been modified, and now when this metal ions forms, they get solvated, because water is a polar molecule, and because of that polar molecule presence, this positive charge is solvated by water molecule, and on the metal surface, since there are negative charges, the water molecule would get attracted depending on what charges are there on the metal surface. If it is negative charge, in the case what we have considered here, the water molecule will be distributed like this, sorry, this is plus, and this side would be negative charges. So, like this rearrangement of water molecules takes place. Now, the center of this particular water molecules, which are close proximity to the charged metal surface, and the center of this positive ions, solvated ions, positive ions, close vicinity to the water molecules which are arranged close to the charged metal surface, that becomes my OHP and this is my IHP. And because of this situation, the double layer, this is becoming my double layer, and that also leads to a potential difference, and also finally it would lead to electrode potential. But this is a advanced level of consideration of the surface. We would stay on this preliminary consideration of double layer, which is Helmholtz double layer, where we do not consider this solvation as well as water molecule, polar molecules distributing close to the charged metal surface depending on the charge of the metal surface. And if it, for example, if it is positive charge, then this becomes, so this water molecule would be like this. Instead of positive charge is close to the metal surface, negative side of the polar molecule would be close vicinity, would be directing towards the metal surface. So, now if we consider this particular situation, we can constitute like this. This is IHP and this is OHP, and this is metal and this is N plus. or we can call it as reductant, or we can call it as red, and this is nothing but oxidant or ox. So, Mn plus Ne equal to M, or ox plus Ne equal to red. And when this metal goes to metal ion or metal ion goes to metal, they would not go straightway like this. Since it is a thermally activated process, they will go over a energy barrier. And this they are on the same value. If we consider G, free energy with distance, so they will be on the same plane when I equal to I0. Why? Because if I consider the rate, forward rate and backward rate, so let us say this is my forward and this is my backward. So, rate R in terms of, if we consider rate, or we simply say R forward, equal to, we can consider it to be same as R backward, and when this situation arrives, it reaches equilibrium, or it calls it, we can call it as R0. And rate of, if we consider rate in terms of moles per unit area per unit time, so this would be equal to I divided by NF. We have already seen this particular formula. So, this turns out to be I forward is nothing but IC, backward is nothing but IA, IC divided by NF equal to IA divided by NF equal to I0 NF. So, then it turns out to be IC equal to IA equal to I0. So, that means the rate at which forward reaction happens, the similar rate the backward reaction also happens. Now, if this barrier is nothing but delta G star, and if we consider N1 or N prime, or I would say N1, let us put it as capital N1 in order to differentiate between this N and this N. This is N1, this is N2. This N1 and N2, N1 is number of moles per unit area on metal surface, or rather IHP, and N2 is equal to number of moles per unit area on OHP, that means the center of the metal ion aligned in front of the metal surface. F1 is nothing but, or the fraction N1 goes to OHP from IHP. So, this is nothing but oxidation. F2 is the fraction of N2 goes to IHP from OHP. and nu 1 is vibrational frequency of metal atom and mu 2 is vibrational frequency of metal ion, then we can write this R forward equal to N1 nu 1 F1 exponential minus delta G star by RT. Why? So, this is as per classical rate theory, and then multiplication of these quantities, this is basically this entire equation indicates the rate of metal number of moles of metal atom, metal going to ion formation, and this is basically a thermally activated process. It indicates that metal atom should jump over this barrier and then should go to the OHP. Similarly, backward reaction R B would be N2 nu 2 F2 exponential minus delta G star by RT. Now, if I consider that whatever metal atom goes to the metal ion surface, everything gets absorbed there, or the metal ions which are getting reduced, they all will deposit on the metal surface. So, then F1 equal to F2 equal to 1. So, since this is a fraction, so this becomes 1, because whatever metal ions are forming, they are going to the OHP, or whatever metal ions are reducing, they are going on to the IHP. Now, nu 1 equal to nu 2 is of the order of 10 to the power 13 per second, and N1 and N2 what we have decided, let us say N1 equal to N2 equal to N, which is number of moles of metal ions or either the metal atom, metal, those are converting to either metal or metal ions. So, that means for both the situation going to M n plus or M n plus going to M, both the cases this becomes similar number, because we have assumed that whatever metal ions are forming, they are getting absorbed on the metal ion surface, which is OHP, or whatever metal ions are reducing, they are also becoming part of IHP. So, then I can write R f equal to R b equal to N f nu exponential minus delta G star R t. Now, we know from the previous discussion, as we have seen here, we can use this equation. So, we know R f equal to R b equal to R 0 equal to I 0 by N f. Now, since we are considering that they are jumping over the same barrier, this is same, this all factors are same, that is what they can be equated. So, this equal to I 0 by N f. So, I 0 equal to I 0 by N f. So, I 0 becomes N f N f nu exponential minus delta G star by R t, and here f is considered as 1. So, I can remove this f. So, it becomes N F N nu. This is an important derivation, because this will be used up when we talk about polarization. So, we have an expression of I 0 with reference to the activation barrier, which is delta G star. Now, we have already termed another, and you see this is also becoming moles. This is current density. Our current density, we can relate it to corrosion rate or deposition rate. So, this is not same as corrosion rate, but it can be related to. Now, we have used one term called polarization. So, when we talk about polarization, it means that it is a shift from the stable value. Now, we see that when m n plus plus n e m, this is reaching equilibrium, so we have a potential, which is of course giving a situation of I 0, which is exchange current density, and if we have maintained standard value, it would be E 0. So, that means activity of m n plus equal to 1, temperature equal to 25 degrees Celsius, and pressure equal to 1 atmosphere pressure. So, then it becomes E 0, E 0. So, if this equilibrium is disturbed, and how can we disturb? This is I C, this is I A with a negative sign. Let us say I supply little extra negative current. This negative means we are supplying little extra cathodic current, which is opposite to the anodic current. So, then this reaction would happen at higher rate. So, if it happens at a higher rate, that means this reduction process happens at a higher rate. In order to maintain that reduction current density, it means that the electrode potential would switch to the negative side. So, why negative side? Because when it switches to the negative side, this metal surface is becoming more and more negative, and that is why the electron supply of electron to this reduction process would become easy. So, then its potential becomes, let us say, E 1. Now, the polarization would be, this is called polarized electrode, and that time the value of the polarization would be E 0, because now we have switched from E 0 to E 1. This is also negative, since the potential goes to the negative side, and this is the value of polarization, or we call it neta C. C is nothing but the cathodic. Similarly, if we supply anodic current, then the potential, this anodic reduction, anodic process will be at higher rate. The way we have discussed here, the electrode potential would increase from the standard value or the equilibrium value, and we also call it as polarized electrode, and that time if the potential goes to E2. So, E2 minus E0 is the positive quantity, since the potential has moved on the positive side, because we are actually taking this oxidation process at a much higher rate. So, this becomes the value of polarization. And when we see that the potential increases from the reduction potential at that equilibrium condition, we call it anodic polarization, and when it is termed as neta A, and when we have this situation we call it cathodic polarization, and potential drops from the equilibrium value, and the entire this polarized situation arrives because of polarization. And this NC or NA, they are the measure of polarization, or we call it over voltage, and this unit is nothing but in volt. So, from this particular information or the discussion, what we see that the polarization happens because of the supply of extra current either in the positive side or negative side, or either extra cathodic current or extra anodic current. And if we send extra cathodic current, the potential drops from the equilibrium potential, which is E0 here, and when we send extra positive current, or we call it anodic current, then the potential increases from the equilibrium potential, which is E0 here also, and the difference in that potential we call it the measure of potential, and in this case it is cathodic over polarization, in this case it is anodic polarization. And now in the next lecture we would get into this polarization part and then try to see the relation between this over voltage and current density. Let us stop here. Thank you.